Here we look at an example of putting a set of ordinary differential equations into state space form. Here we're presented with two ordinary differential equations. These are actually nonlinear equations that we can still put into state space form. We have one independent variable t, and we actually have two dependent variables x and y. We also have the first derivative of y, and we have the first derivative of x involved in these two equations. So the rule is to establish what we need as our state variables, we have to look at the highest derivative of each of our dependent variables and take one fewer than that highest derivative. So starting at x, we have an x dot term, and that's the highest derivative, which means that x is going to have to be one of our state variables, and just x. We're looking at y dot is the highest derivative, so one derivative lower is just going to be y. So for our state variables, we have y as one of them and x as the other. Again, notice it's different than the previous example where we had x and x dot. In that case, we had an x double dot term as in one of our equations, so we had to take one fewer than its highest derivative. In this case, x dot's the highest x derivative, y dot is the highest y derivative. If I take my two state variables and I differentiate them, I now have x1 dot is equal to y dot, I have x2 dot is equal to x dot. I can now rewrite my two equations in terms of my state variables and their derivatives. Okay, so again, remember the rule, if I can write something as just a state variable, I must. It's a little bit less involved than we had in the last case. So here, the only way to write y dot is as x1 dot. The only way to write x is as x2. So that's decided for us. Minus x2 times x2 x1. Again, the only way we can write x in this case is x2. The only way to write y is as x1. Plus 7x1 equals 16 cosine 2t. And the second equation, the only way I can write x dot is as x2 dot. Minus 4 times x1 equals 0. So I've rewritten these two equations in terms of my state variables and their derivatives. Again, the next step is I need to isolate the derivatives of my state variables. In this case, x1 dot appears only in the first equation, so I need to isolate it in that first equation, and x2 dot appears only in my second equation. So in the first equation, I can divide through or I can move the 2x2 x1 to the right-hand side, I can move the 7x1 to the right-hand side. I can then divide through by 4. I can then divide through by x2 so that I isolate x1 dot on my left-hand side. If I look at the right-hand side, I have state variables, x1 and x2, that's okay. Even if x2 is in a denominator, that's okay. Plus 4 times cosine 2t, that's also okay on the right-hand side. What I can never have on the right-hand side is a derivative of a state variable, which I do not. And then my second equation, I just had to move the 4x1 over to the right-hand side, and now I have my expression for x2 dot is equal to 4x1. So the end result is I took those two state variables, and I've now solved for their derivatives. And now this would be something that in the next step I can put into my solver in MATLAB, and I can solve for x1, and I can solve for x2, or the values of x and the values of y.